Hi everyone, welcome to Pi and AI Tiger event hosted in partnership with deeplearning.ai. I'm very excited to have you and thank you very much for joining us. I'm Nyandwi, a machine learning engineer and events ambassador at deeplearning.ai in my city. Pi and AI Pi and AI are a series of deeplearning.ai events which are hosted all over the world in order to help people learn about AI and machine learning and be able to talk with industry experts. This is our third event. Since last year, our previous events were about breaking into AI and building career in data science. The recording of this event can be found on our streaming channel. And today, I want to take a leap forward and see what happened in self-driving car. I know that you are very excited about this because self-driving car is a major and exciting industry where AI and computer vision are a major technology. I'm very honored to be with Vladmir Haltakov, who is self-driving car engineer in BMW Group. If you are very active on Twitter machine learning community, you probably know Haltakov because he's actively sharing some interesting projects to the rest of the community. And it's actually what sparked me to invite him to be our guest today. So as a reminder, right after this event, you'll get an email from deeplearning.ai inviting you to fill the survey and get the 50% off on deeplearning.ai courses. So please check that out and get to start some courses if you're interested in learning about AI. And if you have questions for Haltakov or events in general, you're welcome to drop it in comments and we'll have time for that. Without further ado, I would like to welcome Vladimir to walk us through AI and self-driving car. Vladimir, welcome and thank you for joining us.
Hi, everybody, and thanks for inviting me. It's really a pleasure to talk to you on this event. So let me share my presentation, and we can get going. So, give me a second. Yeah. Okay. Yeah. So thanks, John, for the introduction. Maybe I can say also a couple of words about myself. So yeah, I've been working for more than 10 years at BMW now. My background is in computer vision machine learning. I did my PhD at the Technical University of Munich, also together working at BMW. And in the beginning, I was working more on computer vision based driver assistance systems, and worked on a couple of projects that are now in production in millions of cars. yeah, so our functions are launched. And the last years I've been working more involved into the self-driving car project of BMW, and specifically doing localization of the car in an HD map. And as Sean already said, I'm active on Twitter, writing a lot about machine learning. I also have a blog which you can check out. Not so active there, but yeah. So I I want to talk to you today about more or less about three topics. The first, I want to give you like an overview of the self-driving car industry to see who is doing what there. Then I will explain how a typical self-driving car works and deep dive into two specific topics: the different sensors used in self-driving cars and the different computer vision algorithms. And specifically, we are going to look into object detection. And in the end, I wanted to give you like an overview how a self-driving project works, what are the different roles, different people working on it, and to give you some advice if you want to become a self-driving car engineer and how you could do that. So let's get an overview of the industry. Like, everybody's talking about these different levels of autonomous driving. So I wanted to give you like a short explanation what they are. Like the first level is not really a level. Like level 0 is basically no automation at all. Like it's just a normal car, but the driver is supposed to drive and do everything by himself. Then we go to level 1, driver assistance, where the car starts doing some things by itself. Like, for example, throttle and brakes. There's a typical examples are like systems like adaptive cruise control, which keeps the distance to the car in front, but the driver still needs to steer. Then level 2 is interesting. It's more or less where almost everybody is at this stage, where the car can do all the driving for you. It can accelerate, it can brake, it can steer, but the driver is still responsible. So the driver needs to monitor and detect if the system is doing something wrong, because the system doesn't know that it's doing something wrong. And then this is the gap between level 2 and level 3 is like the biggest gap between the levels, because this is where responsibility shifts from the driver to the system, right? And in a level 2 system, if something happens, it's always the driver responsible. And in level 3, it's the car. And this is a pretty significant difference. Like, so now again, the car is doing all the driving, but it's also responsible to monitor the surrounding and detect if there is a situation it cannot handle. And then we still have the human and the driver as a fallback. So the car detects that something's wrong, that it cannot continue. It needs to hand back the control to the driver, but needs to give him some time, something like 10 seconds before he takes over. Now, when we go to level 4, there is the main difference is that there is no human driver as fallback anymore. So there doesn't need to be a driver, the driver seat at all. So this is like, for example, what Waymo is currently doing with their robotaxi program. And level 4 is not limitless. So they're like the so-called ODD, where it's basically a set of defined situations where you can drive. For example, it could be just one city, just particular streets in the city, just particular weather conditions, and so on. But inside of these conditions, the car needs to handle everything by itself. And then level 5 is like the ultimate level where the car can drive everywhere without restrictions in any kind of situation and can handle everything by itself. So let's take a look at the major players in the industry, and the list is not complete, but it kind of gives you an orientation what people are doing. Like, we have first the traditional car manufacturers like BMW, Mercedes, Audi, and they're basically all currently at level 2. Like basically every car manufacturer now has good level 2 systems, and there are a lot of companies working towards a level 3 automation, which they can want to build into their cars and sell it to customers. And this is exactly what I'm working on at BMW, making this jump from level 2 to level 3. There are also other companies that approach the problem from a different point of view, more or less. They start from the high levels and go back. Like Cruise and Waymo, they're currently the only ones allowed to drive without a safety driver, but in very specific situations. And the interesting thing about Cruise is actually that they were bought by GM, by General Motors, and they also developed some level 2 functions, which they sell in their consumer cars. Then there is a whole bunch of companies like Zoox by Amazon, Aurora, Waymo, Argo, and so on, that are directly going towards level 4, level 5 automation, like skipping all the levels before that. Tesla is a very interesting example because what Tesla has today is a level 2 system. Right? The driver is always responsible, and they are pushing a lot towards level 5, making the big jump there. And Elon Musk is promising this for some time, but they're not there yet. Another interesting company is Comma AI, which actually sell aftermarket devices that you can build in your car and make it, they call it self-driving. But again, it's only level 2 system, right? Another interesting company is Mobileye. They are basically a supplier for many of the traditional OEMs. For example, BMW has a big cooperation together with Mobileye and Intel. But they're also developing their own system for level 4, level 5 autonomous driving, which they probably want to sell to companies. NVIDIA is a similar player. They're a newer player, especially with the boom of deep learning. NVIDIA has a very strong platform, so they're also pushing a lot to get level 4 system on the market. And then they're like the traditional automotive suppliers like Bosch, Continental, Veoneer, which all have level 2 systems, also working on the higher levels, but mainly on level 2. And like everybody now, like everybody talks about level 4, level 5. This is like the favorite topic. I just want to point out one thing. Like the level 1 and 2 systems, they don't get too much attention, but they're like extremely important, and not only for comfort, but also for safety. Like, for example, in the European Union, every new car that is sold now needs to pass very strict tests for the automatic system to get this 5-star rating for the safety. Like we had the crash tests in the past. Now, passing the crash tests is not enough. You also need to have good automatic braking. So this is like an example of the test they're doing, like braking on cars, on pedestrians in the night. So this is all the car braking automatically. So these systems really contribute to make the roads safer, right? And they don't get so much attention as the more sexy level 4, level 5 robotaxis. But this is a reality today, and this is mostly the same technology. So now I would like to get into how actually a self-driving car works. This is a typical pipeline, which a lot of companies are doing it the similar way. Like you have sensors, then some kind of perception of the environment, localization in the map, prediction, planning, and control. And I'll go deeper into each of them, but just take a moment to think about where do you think AI is used in these systems? And the answer is basically everywhere. Now, AI and machine learning in particular is such a fundamental part of every step of the pipeline that it won't really be possible to do anything without machine learning in AI in the self-driving car industry. So let's take a deeper look now at the different parts, like the different sensors. I'll talk more about them in a minute, but I'll just give an example here based on the camera. Then the task of the perception is to basically recognize what's around us, like where the lane boundaries, where other cars, pedestrians, traffic light signs, which is then a basis for the decision, what does the car do next. One important thing is the localization in the map, because a self-driving car needs to know where it's going. And many companies also use a high definition map. This means that it's not on the level you're used to from Google Maps or something, but it actually tells you where are you exactly in the world. And this is up to a couple of centimeters accuracy. So there is one company that famously don't want to use the HD map, but that's Tesla. But basically everybody else is using it. So after that, after we know where we are, we know what's around us, a very important step is prediction. So we want to predict where other people, where other cars, other pedestrians are going, like to have some kind of idea what the other people will do around us. After we know all of that, we need to plan our own trajectory in the planning module. So we need to decide, do we accelerate or we brake, and where the path where we drive along. And the last step is actually executing this, rotating the steering, giving throttle or brakes, and so on. This is one way to do it. There are companies pushing for a bit different direction, the so-called end-to-end approach. So it basically, you get the sensors on one side, you feed them the raw data in a huge neural network, and the neural network has the output, which is how much I turn the steering and how much I accelerate or brake. And this kind of works. NVIDIA is one of the companies that are pushing this approach. And this is like a short video showing their car driving actually quite well with this. The problem with this approach is a little bit that you can actually train it very well, because you just need people driving. So they just by driving, you generate the ground truth data, so you can train this machine learning, train this network. The problem is it can then react only situations it already saw. And there are a lot of rare situations which you cannot encounter or you don't want to encounter. Imagine like a child running across the street. So if you want this system to break on it, it kind of needs to have seen such a situation. While in the more traditional ones, you can encode rules like say your perception sees a child, and the prediction you see it's crossing the street, so you can now have a rule that you need to break to avoid collision. And there are actually architectures that kind of combine both worlds in some kind of hybrid, which are also very interesting. But I'll get back to the more classical pipeline now, and today I will focus on these first two parts. It's also where I have most of my experience, so I can go deeper. And yeah, it's also quite a lot of information. So let's wanted to give the talk a little bit of focus, so we can go deeper on some topics. Let's take a look at the sensors. Like there are three main kind of sensors: the camera, the LiDAR, and the radar in the car. So this is some example of cameras, like the one those here are like the show a pointer. Yeah, those here are like typical automotive cameras that can be easily integrated into the car. And there are companies like Waymo, for example, having this rooftop boxes with many cameras. Like Waymo uses the latest generation, something like 29 cameras. And this is like a video I took from it's by Mobileye, where they show you like typical detections of an automotive camera. Like you see detection of the free space around the car, vehicles, traffic lights, traffic signs, pedestrians, and so on. So this is something quite typical that you can do with the camera. Then we have another sensor, it's the LiDAR. So you probably know mostly this kind of LiDARs, these huge rotating things on top of the cars, which provide like a 360-degree point cloud. And there are like many variations. Companies like Waymo actually produce their own LiDARs, this one. But there are also LiDARs like this one, this is the Innovis LiDAR, which can actually be integrated very nicely into the grill of the car. And you don't need to put them on the top. They provide then only, yeah, they can see only in front of the car, but still they're very useful. And this is how a typical 360-degree LiDAR looks like. This is one video from Waymo. You can see here the circles are basically the scans of the individual lasers, and the LiDAR basically tells you how far away each point is. And you can then build clusters like these boxes here, where we have the different objects. Yeah, and the LiDAR is very good at measuring distance. And the third main sensor are the radars, which work on a different principle. They use the Doppler effect to determine distance and relative velocity between objects. And you have like these like examples of traditional automotive radars that have been built into cars since 20 years or something. And there is now like a new generation of LiDAR, the so-called imaging LiDARs, which provide much more resolution and are almost more like a LiDAR. So it's very difficult actually to visualize the radar echoes, and I actually couldn't find a very good public video on that. But to give you an idea what the radar sees, and this is like a very more simple traditional radar. This is a video actually from the Tesla camera and shows the Tesla detections, but this blue squares you see, they are the echoes from the radar. So what you see is they reflect especially metallic objects, like we get a lot of points on the cars. But you see resolution is not great. But again, it's very accurate, measuring distance and velocity. And now if you put them all next to each other, you see that every sensor has different advantages and disadvantages. Like the cameras have the biggest resolution. They can do very well object classification and can detect the object semantics. Like even if the LiDAR can detect that there is a traffic sign, it cannot read what it is. Is it like a 60 speed limit? Is it 80? Is it a stop sign or no parking sign? This is something that only the camera can tell you. Then the camera, on the other hand, is bad at distance estimation and terrible at velocity estimation, where actually the LiDAR and especially the radar shine. Also, night is always a bit more difficult for the camera, especially if you don't have headlights. Like, for example, if you have camera looking backwards. And LiDAR and radar are actually quite good. And there are different weather conditions that are bad for different sensors. Like the camera has problems with low sun, with heavy rain at night. The LiDAR, on the other hand, has a problem with spray from other cars. and radars have problem if snow starts accumulating in front of the sensor. So in the end, you see that there is no perfect sensor. Every sensor has weak spots. And that's why one of the best strategies is to combine all three of them, to have like the best of four worlds. And there are different strategies by the different companies. I clustered them in like three strategies. Like first one is what I call the robotaxi strategy. This is like example here is Waymo. So the idea is to put as much sensors as possible on the car. You see, they have 5 LiDARs, 29 cameras, and 6 radars. You see the big box on the top here, the side LiDARs, one in front. So it's actually, yeah, but they're basically brute forcing it, putting as much sensors in as possible. And this is like other examples you can always see on these cars, like the roof, top boxes, full of sensors all around the car. This one looks like a giant iPhone, is the one from Apple. Then there is another strategy, the more consumer vehicle strategy, I call it, which is more the traditional car manufacturers. So this is actually one of the BMW prototypes for the level 3 project. And you see that everything is nicely integrated. You don't have these big boxes. Yeah. So it's much more cleaner, and this is what you expect when you sell a car to like private people or consumers. You cannot put like such huge sensor boxes on top. And then there is the Tesla strategy that really push for almost only vision. Like they have their 8 or 9 cameras and a radar, but they don't use LiDAR. And Elon Musk is famous for saying that LiDAR is a crutch, and everybody using LiDAR is doomed. And another company with kind of similar strategy is Coma AI, mostly because they are like limited to the sensor that traditional cars have. And again, putting this in a comparison, it's different approaches. And every kind of company chooses the best approach for themselves. Like Waymo going for a robotaxi, they want to reach this goal first. So they put as much sensors as possible. That's the fastest and most safer way to go to self-driving. It's again difficult to integrate in a normal car, but again, Waymo is not interesting into building like a normal car. It's more in the robotaxi direction, and it's very expensive. Like the traditional car manufacturers, they go for safety by providing a lot of redundancy, but they want to have the system integratable and not too expensive. The problem is that it may not be really enough for level 5 system. And the vision only approach from Tesla is the cheapest, but it heavily bets on computer vision getting good enough. And when it's kind of true that we drive without LiDAR, without a radar, or just using our eyes. The problem is that computer vision as of today is not so far as as human vision. So the question is if you get as good as needed, as fast as that. In the time frame they want to realize this. And the lack of redundancy could be a problem in this case. Let's go now to perception. I will mostly focus on the computer vision parts and talk about the different kind of tasks, different challenges that a car needs to solve to drive fully autonomously. And I'll try also to list some methods here that are typical for this task. I think the first one, and maybe the most important one, is object detection. So basically you want to detect where are other cars in the scene, what traffic lights, signs, some markings on the road. So that just, what's around you, and typical methods are RCNNs or YOLO. And we're actually going to look more in detail into YOLO in a minute. Another approach is to say, okay, I don't want to take specific objects. I want to basically classify each pixel in the image. So for each pixel, you say, is it a car? Is it a plane boundary? Is it a pole? Is it the building? And so on. And they're like fully convolutional networks, something that enabled this kind of work to be done with deep learning as well. And since then, deep learning is again dominating the field of semantic segmentation. And when you do that, it gives you like the possibility to do some other things like do lane detection, the lane boundary detection, to get an idea where is the free space, so where the car could actually drive without like, hitting a curb or another object. Then another important point is distance estimation. So it's not enough to know that there is a car in front of you. You want to know how far it is. So there are different methods. Like there are a lot of classical methods for tracking, and for example, common filters that can give you an estimate of the distance. But again, deep learning is taking over this field as well. And one example method is deep sort, which can do this using deep learning as well. And again, another approach similar to semantic segmentation is to say, okay, I just want to know the distance to every single pixel in the image. And there are solutions like using a stereo camera, structure from motion, but they are difficult to do. Stereo cameras are expensive. And now it's like since 2-3 years, more or less, there are a lot of methods for so-called single frame depth estimation using self-supervised machine learning, which is really cool because you don't need any ground truth data. You basically, the network trains itself more or less to know the distance to each object. So they're like very powerful methods, and we see already companies, this Tesla has something like this already implemented into their full self-driving beta. And Tesla has also another interesting approach, the so-called bird's eye view network. I mentioned before that most companies rely on high definition maps to get some kind of understanding of their surrounding. Tesla does this purely from vision. So what you see here in the display are the lane boundaries and the junction topologies, which are detected purely by vision. And it's really impressive to the extent that they can do that without a map. So it's actually quite cool. Basically a neural network taking all the cameras and predicting the layout of the junction and the lane boundaries around you. It's a so-called bird's eye view network. So similar to cameras, you can also do very similar things like object detection free space in LiDAR images as well. This is one example where there are also like network architectures like PointNet, for example, which does the object detection in this kind of images, this kind of point clouds that you get from a LiDAR. And there is one other example actually from the BMW project on sensor fusion for detecting the free space. So what you see here are like the green is the space where the car can drive, and red are some kind of obstacles along the road. And these are different sensors. This is a radar looking in the front. These are like 4 smaller radars around the car. This is what you get from a laser scanner and from a camera. And sensor fusion basically takes different inputs and creates one representation, which is better than every individual one. You can see here, this one is much more stable than any of the individual sensors alone. So I chose one topic to go a bit deeper to see how it works in more details, and it's object detection, because I think it's one of the most important ones. I took a method called You Only Look Once, YOLO, which is more or less state of the art for object detection. And this I run this image through it. And as you see, it did pretty good job detecting the traffic lights, pedestrians, cars. Yeah. So how does it work? Basically, need to it splits the image into small grid cells. This example, it's like 7 times 7. And then each cell does two things. The first one is to predict the class. So basically every cell needs to say what's inside. It's like the more typical image classification problem. So this cell says I'm a dog, I'm a bicycle, I'm a road. So you can see the predictions here. Then the second thing each cell does is to have a proposal for a bounding box. So each cell generates a couple of bounding boxes that are centered in this cell to try to, put a box around an object that corresponds to this cell. And then there is a process of selection that leaves only the ones that have the highest scores. And this just gives you an object detection and tells you where it is in the image. It's a big convolutional network that does this, using actually many layers of convolutional max pool layers and alternating between, in the beginning it's 7 by 7 convolutional kernels, but then alternating between 3 by 3 and 1 by 1 convolutions. And it gets smaller and smaller on the image size until they have a fully connected layer. And in the end, it's very interesting how they model the prediction. It's like you see it's a 7 times 7 output, which is the grid cells, and they have 30 elements. And the 30 come from, you have 2 bounding boxes predicted from each cell. So you need 4 parameters to describe a bounding box: the center of the bounding box, the width, and the height. So 2 bounding boxes with 4 parameters is 8. Then you have 2 for each bounding box. You have a confidence. That's another 2. And then you have for each cell the cross probability distribution. So the probability that this box is a car, is a dog, is a whatever. They have 20 classes in the paper, so that's another 20. So this gives you like the final output of the feature vector. Now this is like a brief overview of the architecture of YOLO. And the nice thing is that, like other methods, they usually have a first pass to detect some kind of regions, then they have a second pass looking again at the image to classify each image, and then a third pass to select. The nice thing about YOLO, that's also why it's called You Only Look Once, is because you do this all in one pass and you optimize it all at the same time. Oh, it's a very powerful method. It's very fast, and it provides some very, very nice results. So yeah, so we talked about, until now, we talked about how a self-driving car works. But I want to give a bit broader context about how a self-driving car project is organized. Because a lot of people say, okay, I'm a self-driving car engineer, and it sounds like this is one role and there's like one predefined job and everybody does it, but it's not like that. There are many, many different roles in self-driving car projects. I just listed here a couple of them, and they all require very different set of skills. So if we look into details in a couple of them, like one, I think most people, when they hear self-driving car engineer, they think about something like a computer vision, like a machine learning engineer. You're building models for perception, for sensor fusion, for planning, control. You evaluate different model architectures, try different parameters, evaluate some KPIs, and there are a lot of people doing that in the self-driving car project. But it's not only that. Like typical skills required here are C++ knowledge and Python. Like as soon as you do program something that is supposed to go into the car, you need C++. And Python is often used for training, for evaluation of different parts, for building prototypes, but not really for deploying something into the car. And knowledge of machine learning frameworks like PyTorch, TensorFlow is important, algorithm data structures, and of course, general programming skills. And computer vision engineers is also something that I think a lot of people can imagine what they do. We talked a lot about the different challenges for computer vision, and there are people that need to do that. It's similar. I mean, nowadays, computer vision is, let's say, 90% machine learning. So it's kind of similar with the machine learning profile, but still there are like more classic algorithms, especially for distance estimation, that are interesting. Yeah, so similar skills required. And then we move to some different kind of jobs, like big data engineers, like a self-driving car. All these sensors, they generate like huge amounts of data, like more than 1 gigabyte per second. So imagine long test drives can easily go into the couple of terabytes. So this is a huge amount of data that needs to be processed very efficiently. And so this is like an image actually from the BMW data center, where it needs to store a big amount of data, it needs to process it, or you need to extract the information you want from it. And big data engineers also building applications that enable the other developers to work with the data. And there the skill set is already a bit different. Like data frameworks usually use systems like Hadoop and Spark. So they use more Java and Scala for programming. Again, algorithms, data structures, programming are important skills. Then simulation is another very important topic for self-driving cars. So it's again a different set of skills. You won't be running a real-time system in the car, but there are other things that you need to be careful about, like having the right models, the right simulation environment, and so on. And then there are like like the testing engineers. So their job is to build up the cars, to like prototypes, to wire all the sensors, to organize everything in the car. So this is one example actually from one of our prototypes. You see the boot is full of measurement equipment, of prototype sensors, of the compute platform we're using in the more early stages. And they need to think about how to develop tools to use all of this, to visualize what's happening in the car, to perform test drives, to evaluate the test drives. So it's again different set of skills, more like the communication on the buses in the car. Testing methodologies are very important, and then like general software engineers is like, I think this is kind of one of the most important things. There's a huge need of software engineers in the project, because there's a huge need to implement communication between ECUs, a lot of internal libraries and frameworks. The human-machine interface is very important. Logging, tracing, and like implementing specialized algorithms for some particular task. Could be localization, could be some part of the control, the planning. So it's really, really important to have skilled engineers, again, mostly C, C++. It's good, important knowledge of software architecture and design, writing clean and maintainable code, testable code. So these are important things. And there are also like more exotic roles, like safety engineer, because safety is extremely important when you have a 2-ton machine driving 130 on the highway by its own. You really, really want this to be safe. So there is a lot of work there doing analysis of critical system, functional safety, safety in use. different methods for validation, verification. How do you prove that it's actually safe? There are a lot of formal methods to prove it, also a lot of statistical methods. There are a couple of safety standards in the automotive industry that yeah, you need to work with. So this is again a very different set of skills. So yeah, my main message is there is not one single rule, and there is place for all kind of skill set, even like things like web developers. There are a lot of tools we're using that are based on web technologies. And for example, take a look at Cruise developed also one such tool for visualizing self-driving car data. So it's kind of a very diverse ecosystem and a place for a lot of skills. So yeah, I want to end with some kind of advice because a lot of people on Twitter DM me and asking how do I become a self-driving car engineer. So I want to give you some tips. I think the most important one is first focus on the general programming skills. I think this is more important than having machine learning knowledge or computer vision, because it's usually easier to learn this stuff than to become a good software developer. So we also hired people that weren't that good at machine learning. They were still learning, but they're very skilled developers, and this is usually the bigger advantage. Then testing that is very, very important because of the safety aspect. So learning about different testing methodologies will help you get a job in the industry. And machine learning that it's already used in a lot of places, so it's definitely a bonus if you have it, but it's not required for every position. So said positions are very diverse, so there's place for a lot of different profiles. And similar with C++, it's also good to know, but also not strictly required. And so one way to enter the industry is to tell some people that even if you don't have a lot of experience in the other parts, like many of the companies are actually doing not only self-driving, but other things as well. So it's always a good idea to, if you want to enter the self-driving car industry, to look for a job at a company that's not necessarily in the self-driving car project, and then work for some time, and then look to transfer to the project. And actually, I did something like this. I was at the beginning more on the driver assistance side, and then moved later to the self-driving car project. Yeah. And yeah, this is also a list of useful resources that can help you get started. I see how I post it in the chat maybe after that, or I'll post it on Twitter as well for sure. Like list of online courses and nano degrees from Coursera and Udacity. There are also a couple of simulators that you can already download freely and try out different things without having an actual car. And they're kind of very cool data sets with different tasks, especially Kitty, the benchmarks from very different things like object detection, semantic segmentation, and so on. And also Kaggle competitions and resources are always a good way to gain some experience. Yeah, and then I just have a fun video, like a lot of people talking about self-driving car, and this is what you can do as a self-drifting car. Okay, so now it's time for questions.
Thank you so much, Vladimir. That was really a deep intuition about AI and self-driving car. This is really cool. I like that.
Thank you.
We have some few questions on chat, um, on live chat. I try to go through them. It's probably right too, which seems to be answered, but maybe it would be good to kind of reinforce it. The first one is, do we have simulators for self-driving car we can use?
Sorry, I kind of I wanted to look at the chat, but I get the sound mixed up. Can you repeat the question? Sorry.
Yeah, it was saying, do we have simulator software for self-driving car we can use?
Yes. So two of the links are exactly that. So there is the Carla simulator, which is developed by Intel, and it's actually quite complex, and it's free and open source. And you have one by Udacity, which is also like open source, and everybody can use it. And then you can do perception, you can do car control. Yeah, so they're actually quite good open solutions.
Another question is, it seems to be a deep question. In vision only, as you said, it is not capable to reach level 5. So what change or improvements can be made to achieve to get to level 5?
I believe one day it will be possible, because I know humans are approved that vision is enough to drive alone. But I think computer vision needs to get much better. And I think one of the biggest challenges is like all the different variant, all the possible situations that you can encounter. Like computer vision is very good at solving specific tasks like detecting cars. This is something that's more or less solved. Computer vision systems are very robust there. But there are like a lot of edge cases, this long tail of very rare events, which you need to handle, which computer vision doesn't generalize well enough yet. Like you could have we had actually one real case where a car encountered a dead pig on the road. So there's no classifier for dead pigs, so you need somehow to handle that. I think this is the biggest challenge, to make computer vision generalize well enough to be able to do these kind of general tasks. And someday I believe it will happen. Nobody knows when, and Tesla hopes to solve this by using huge amounts of data. But it's still an open question if they will solve it into the next year. So it may take 20 years or something.
Yeah, thank you. This I think question is cutting to ground, which is nice. The next question is, what are BMW goals overall in terms of level of automation they want to achieve? Could they try like robotaxi way more in order to get to level 5?
So what BMW announced the plans to do first. So the strategy is more to do it like one level up, like with level 2, then do level 3 and do level 4, because the task gets increasingly complex. So the goal is for next time is to have a level 3 system on the road, and level 4 comes after that, and so on. So for now, it's level 3.
The next question was asked by Kennedy. He he asked, is the technology for self-driving car going to extend to airplanes or trucks or ships?
Okay, trucks for sure. The trucks is an easy answer because they're also like Waymo, for example, they have one program for the vehicle and one for trucks. And there are other companies that are focusing on trucks specifically. And you can imagine that this being a huge use case because one of the biggest costs in running a truck is the driver, right? Now, airplanes, I don't know, airplanes they're already quite autonomous, but there's just, let's say, there's just much more space in the sky and much less airplanes. So it's kind of an easier task. So I don't see that much technology going into airplanes, but trucks for sure. Yeah.
Let's see what's coming. There's another question. For the part of safety of autonomous cars, do you recommend any online courses or websites or methods used for verification and validation of this autonomous system? I think I'll have to repeat it. For the part of safety of autonomous cars, do you recommend any online courses or websites of methods used for verification and validation of this autonomous system, car, for example?
Yeah.
Especially with especially when we apply deep neural networks and their problem with adversarial examples.
This is a good question. So I have to see. I think I saw some courses for safety, like there are these ISO standards, the ISO 26262, which is actually used for many years already in the automotive industry. So you can definitely get certified on this standard. Now, the other question was very good. I don't know who posed this, but it's probably somebody that already knows a lot about this stuff. And it's a big challenge actually. Like these standards are older, so they didn't think about things like deep learning, machine learning when they created them. So it's a big challenge to combine both worlds, and there are some works to do that, but it's still very, let's say, very open to how you do it. It's a big challenge, and it's actually, I think, there are a lot of open questions to be answered. How do you? There are some kind of ways to work around that. Yeah, but it's not like a really nice solution until now, I would say.
Well, Adere asked, what are the ethics and regulations in this context?
Ethics. We had like a very interesting discussion a couple of weeks ago on Twitter. So I guess with ethics, I don't know what is meant. Probably this trolley problem, like if you can either crash and drive over an old lady or a baby, or drive off a cliff and kill yourself. So is the car responsible for protecting the driver or protecting other people? And this is only my personal opinion. I think it's always the right way is always to first be to do the safest thing as possible, to minimize the damage as much as possible. Because even if you crash, if you manage to slow down enough, it's probably not a big problem because cars are safe today. And then it's always important to stick to the law and be predictable, because it's never only you that is acting. And I think it's very important to act predictably. So if you see you have a crash, it's better to slam on the brakes, stay in your lane, and not start, turning rapidly left or right, because this has much more unintended consequences. So I think this is how this needs to be handled and not programmed like what is more important, a baby or an old lady or things like that. You always need to minimize the damage in total. Stay predictable and do what the law says. The law usually says you're not supposed to leave your lane. You need to stay in your lane, do everything you can.
There's more question coming. I'll go to, I think he continued asking about ethics. Are they well established, and are there any other type of sensors to help grow the level of autonomy beyond beyond camera, LiDAR, and LiDAR? Is it possible to research about any type of sensors, or do you know any new article?
Yes, an interesting question. So there are also other sensors that are not just that much, like ultrasound. It helps you only in a very close vicinity. There are like night vision cameras that could be useful as well. And then there are things like very accurate GPS system, for example, to help you with localization. Yeah, I mean, I haven't seen too much like really new groundbreaking sensors. I think what is more currently the trend is to to optimize a lot of the existing sensors. So there are a lot of work, for example, into these imaging radars, which are much, much better than the traditional radars. There are also a lot of work into specific kind of LiDARs that can also measure the face and somehow estimate the velocity difference. So I think more work is currently going into improving the existing sensors because there's a lot to be improved there, especially in LiDAR and radar. So I think this is the way to go. Yeah.
Fateh asked, what are the difference and the similarities of working on autonomous car and autonomous train? Interesting.
Sorry, what are the different?
Between what is the difference and similarities of working on autonomous car and autonomous train?
Oh, okay. I don't know much about autonomous trains. But I mean, I would say that yeah, the train is easier because it's let's say it's a 1D problem, right? You can drive along the rail tracks and you cannot change lanes or stuff like that. It's you also usually don't have other objects on the rail tracks, and even if they are like trains have huge braking distance, there's probably not much how to react. I know that there are challenges, for example, in localization, because trains do go through very long tunnels, and it's always important to know where your train exactly is. So there are like these kind of challenges. But I would say it's they don't probably have too much in common because the biggest difficulty in cars is actually the other people around you. If you have an empty track, it's not too difficult to drive around and do it very safely. It's the unpredictable behavior of the people around you that's the real challenge, and I think that's not really yeah, the case in trains.
It's hard to predict which object the car will receive. Someone, after thanking you for great presentation, asked how many engineers are involved in BMW and your team, and outlook for the future after the level 5 is soon reached. What skills will be needed? This is interesting.
Okay. So let's see the engineers involved. So there is like a special division in BMW that takes care about the autonomous driving and the driver assistance. So assistance systems. So it's both level 1, 2, and 3. And I don't know the latest numbers, but its ballpark is more than 1,000 people. And there are also other people in other divisions that can help, like for example, when you do control of the car, like the steering and the brakes, there are people specialized for that do it not only for the self-driving project, but also for the like the regular driving. Yeah. So it's a lot of people. And then the level 5 is I first, I don't think that we'll reach level 5 that easy and that soon. I think we've seen level 3, level 4 are, let's say, just around the corner, more or less, in some limited situations. So I think there is a lot of work for level 5. So I won't be too worried about my job. And then after you reach it, it's you never, especially with machine learning, you never develop one system and then you live it and it always works. Like the world changes around us, and you need to react on that. You need to adapt everything to the changing world. And I think there also be a very new use cases after that. Let's say if all vehicles are autonomous, you can start doing some more advanced planning of and coordination between cars to infrastructure communication. So I'm sure there will be a lot to do. And like level 5 will not be like it's reached, and from now on cars can drive forever on their own. You need to continue working on that and adapting.
Kennedy asked a question which I ask myself too when I think about owning self-driving car. Some of our roads in Africa are not really great and are impacted by bad weather a lot. How would a self-driving car overcome that? Or do we even have, I mean, what are even the challenge of having self-driving car in countries with with you know with not developed roads, or what are the challenge around it based on new technology?
Yeah, so it's an interesting question, and I think you see how the companies doing their first focus on the easier situations, like for example, Waymo, they're running in I think in Arizona, where it's mostly wide open roads, going straight, and then a couple of 90-degree turns. So it's like, let's say that almost always nice weather. So it's like the easiest cases. And when you do this, you need to scale. But so for sure, bad roads will not be like the very first challenge to tackle. But I think it's possible. In the end, if a human is able to drive there, at some point in time, a self-driving car will be able as well, I think. And I remember, like, one of the very first challenges for self-driving cars was, I think, back in 2007, the DARPA challenge, where they actually drove through the desert. Like they drove and they had to reach some checkpoints and some destination without any kind of roads, driving to the desert. So it's kind of already been tried in these cases. So I think it's a very difficult case, but in the end, I'm sure it will work there as well.
That sounds promising because I think everyone who is in tech at this point, at some point, think about having self-driving car. So that sounds very promising. Kabanda Kweba asked, who is also one of AI meetup organized.
Mhm.
He asked, do you use ground penetrating LiDAR? And if so, what are their main drawbacks?
Huh. We don't use them, but we actually took a look at them. So it's like I assume you mean radars that like look into the ground and measure the properties of the road and the ground below you. I'm not sure how much I can say, but let's say that there's a very interesting cases. But I think the current state that they're pretty big. So and integration in the car is an important topic. And like having like very expensive piece of equipment on the bottom of your car is usually problematic because you know you drive the car and if you hit it on a speed bump and cause a damage for a couple of $1,000s, it's a problem. So I think this is interesting technology. I'm not really sure it will get deployed soon in cars. Yeah, but it's actually it's an interesting topic. Yeah, maybe it's more relevant for areas if you don't have good roads, or yeah, maybe then it's more interesting to look at this.
We still have one question in chat. I mean, we have time rest for the meeting to end.
Mhm.
So if people still asking some question, we can still take them. There's one from Ridi. That's it. Like computer vision is used in self-driving cars, augmented reality, virtual reality, and mixed reality. And industry needs more computer vision engineers. So what are the opportunities for computer vision engineers in the future? And what's your view on the future of technology?
Mhm. So computer vision is definitely one of the most important parts, and the camera is one of the most important sensors. And you see that nowadays every phone has a camera, and a lot of smart devices start to get cameras like TVs and so on. So I think computer vision is only going to grow, and it's by now already quite a mature ecosystem. So it's very easy to get started. There are great frameworks for computer vision, um, great libraries, and so my feeling is on this is that things will kind of shift a bit from developing methods to having the curation of the data. Like the big bottleneck today is not to have a good deep learning architecture; it's to get the right data. And I think this is where a lot of opportunities lie to figure out clever ways to gather training data, not just there are other ways, just labeling, which is very expensive. If we can figure out a nice way to collect data, it probably open up a lot of applications. And also the second part is we've seen with a couple of recent works, for example, Clip by OpenAI, which are able to tune huge models, which seem to be able to generalize very well. And then the problem kind of shifts to not training the model, but creating the right prompts to ask the model the right questions to get the right answers. So I think this is more or less where computer vision goes. And I think there will also be a lot of just like optimizing for very specific applications, because it's one to have the model, it's a completely other story to have an application that is really usable for the end user. So yeah, I think there's a lot of opportunity in all of these directions. I hope this answers the question.
Yeah, that sounds exciting because a lot of people are really interested in machine learning and vision side specifically, or either natural language, but sounded exciting and promising when, like, clear that there are opportunities. Another question which come now is, would you please explain a little about open problem in self-driving cars and best universities of Europe which are working in this field for PhD? I think you are the best person for this question for sure. I mean, looking back on your journey, yeah.
Mhm. So let me see. So open problems. I think I think one of the biggest challenges in self-driving is like this huge variety of situations that that can happen. Like if you have a good weather, straight highway, and a couple of cars around you, it's not really difficult. It's all the strange things that can happen on the road. And I think working into enabling machine learning to be able to generalize well and handle this situation without explicitly seeing them in the training data set is very important. And otherwise, they're like open, I think, open questions everywhere. Like in the perception, we're still not there regarding robustness of many systems, even like semantic segmentation, depth estimation. There's still a lot of work to be done to get them at the high accuracy level required for autonomous driving. Prediction, I think, still has a lot of open topics because there are like specific models for predicting some things, but especially people sometimes act differently. And planning control, I'm not so deep into that, but I'm sure there are open questions as well there. Now regarding universities, so I think you can in Europe you can pick like the ones that are usually the big ones and the good reputation, and also have a lot of things working into self-driving. I think so. Cambridge, Oxford have a very good groups on computer vision. Similar is Zurich, Technical University of Munich as well. Yeah, so I don't know if they're like very specific ones in Europe, but basically everywhere where you have a good vision lab, you'll find relevant topics, I'm sure. So I think that if you want to go for a PhD, I would do it this way: that if you're interested in a particular topic, let's say computer vision or could be control, look at the papers that come in this area and look at the people where they're coming from, and then you'll find the good labs and at each universities there are.
There's one question I see. It was somehow answered in the presentation. It was fully answered in the presentation, but I remember that some people joined the event in the middle, and I think well, maybe if you can share what you think about it. It's about Tesla strategy of full vision. I think it was asked by, let me try to see, by Ludwig. He asked, what's your opinion on Elon's statement on everyone who is riding LiDAR is doomed? Tesla strategy of vision and LiDAR on.
Yeah, so I mean, I think it's a dangerous strategy to go vision only, because it's like computer vision is not there. So it's vision is not good enough today. So if you go the full vision route, like Tesla, you're basically betting on you getting computer vision, improving computer vision enough for it to replace LiDAR, for example. And the question is if you manage to do it, right? And Tesla, I think, is very bullish on that because they have a very, very efficient pipeline to get data from all the cars they have out there. So they can get huge amounts of data, and this is for sure helping a lot to push the state of the art. But I don't think there's any guarantee that this will work and that it will be good enough in the next, maybe in the next 5 years, maybe the next 10 years, maybe the next 20 years, you don't know. So the much more safer route is taking the LiDAR, and the only disadvantage of LiDAR is the cost. Like, and costs are falling as well. So LiDARs get cheaper and cheaper because more and more cars start integrating them. So personally, I think the better strategy is to use a LiDAR, even if it's maybe not required at the end, but it's the much more safer approach. And when talking about self-driving, and it's a very new thing, I think safety is extremely important to convince people that they want to have these cars. And yeah, so it's kind of a bet, and when you get it to work, and you see most of the other companies are going for the LiDAR because it's an additional redundancy and it's safer.
Yeah, it's really discussed. There's another question. How long have you been working on this technology, and what one thing that shocked you in the beginning, and what one thing you want to see in the future of this technology? This is interesting.
Okay, cool question. So yeah, basically I started 2011, started my PhD in computer vision, working on semantic segmentation. It was not directly for the self-driving car project, but it was like, I mean, the technology is more or less the same. So that's what, about 10 years now. And then I continued working a lot with cameras and machine learning until, let's say, 2019, and then I switched to localization. And what shocked me, let's see, I think it's the complexity. It's mind-blowing how complex such a project is, and how many things need to interact with each other, which need to work in synchron, even not even for the self-driving car, even for the regular car with this kind of systems you have today, like the level 2 systems. You have like something like 60-70 ECUs in the car, and getting them to work all in perfect synchron. And I sometimes like find it mind-blowing how this works in the end. And it's a huge effort of so many people required to make it work. So this is like, this complexity was really shocking. Like at some point I kind of made a list of all the people I need to talk to on a regular basis. It was over 100 people. So for work, you need to talk to over 100 people on a regular basis just to to synchronize everything and make sure it works in the end. So complexity is one of the things, I would say. And what was the last part of the question? What I want to see in the future with these technologies. Yeah, I think it's self-driving is like one of the interesting things, but the other thing is safety. And I think there's still a lot we can do there. I showed you the videos of the cars that automatically brake pedestrians. and other cars, but there are other cases as well. So I've worked on a project, it's actually also in production, which warns you that you don't cross a red traffic light, but there are also other cases with signs. And I think this improving the safety is something that will have real impact um, beyond self-driving cars. And I would like to see this extending and covering more and more cases.
This is a long time. I would like to thank everyone who asked a question in the comments. If some come in 2 minutes, we can see take them. But we also have some pre-asked questions. Most of them were asked during this chat, but there's some maybe that we can go through. This one, which is really somehow strange. I think a lot of people we are very attracted by machine learning, and we sometimes underrate the software engineering, which is the foundation of almost anything in this technology. So I would like to hear your thoughts about machine learning and computer vision. Are them a critical technology in driverless cars? How does that match with software engineering?
So yeah, they're definitely critical technologies. And I think you see this shift, like when a problem gets complex and where it has a lot of data as input, it's usually inefficient for a person to start, tuning some parameters and writing rules. As soon as you get to this stage, it's actually usually better to go to machine learning. And I think you can see that you have a code base and for like traditionally written code, and there are more and more machine learning applications that starts substituting some kind of modules and make them more yeah, turn them into machine learning models. So it will not work for everything. I think not everything will be machine learning, but it start replacing more and more of the code. And I think in the future, this will be like a skill that almost everybody needs to have, is to be able to train a machine learning model, understand how to evaluate it. Because a lot of parts of the code, not only self-driving, I think this is a general statement, will turn into like machine learning models.
You remind me, Andrew, slogan that AI is or machine learning is an electricity, and eventually every company is going to have a need of it in some way. So, yeah. There's one more question, if not two. Image annotation or data labeling is one of the complex and boring tasks which takes a lot of time, and I expect that you deal with it quite often. How do you annotate image at BMW? Is it fully automated or there are humans in the process?
So there are different kinds. So there are problems for which we don't have good enough automated methods. So we have human labeling as well. So we usually do it with companies that are specialized in this, that have trained people and can do this efficiently. But what we always try to do is to find a way to automate things. So there are different ways. One is to, let's say, buy a very accurate sensor that you cannot build into the final car, but you can use it to generate data, like buy an expensive LiDAR or a couple of them and put them on the roof to generate ground truth. But the really nice thing is to find a way to automatically generate, let's say, some kind of ground truth from just driving. And one good example are these self-supervised methods for depth estimation. which don't require any labels. And if you meant not all problems can be solved with that, but there is definitely a push to find more and more use cases you can do self-supervised or kind of automatically get the ground truth. But some kind of problems are still, yeah, unfortunately still require human labeling.
One more question is, it's interesting question too, which we may not think about, but does machine learning model training happen at the edge or in the car, or it's cloud-based?
It's cloud-based, always. So we don't have any use case of training in the car itself. So we rather work on ways to, and we have ways to get all the data from the car in the data center. We do it with our test cars, but we also do it with the fleet of cars you already have in production. So they provide us data as well, but everything is aggregated in the backend, and it's we use, for some cases we use public clouds like AWS, and for some cases BMW has its own data center doing the training, but there's no training on the edge, so to say.
This is a weird question, but could hear about it too. What are some scenarios in which computer vision models powering the car can make weird decisions?
Yeah, I mean, I think the problem, one of the big problems in computer vision is that computer vision systems, they don't look enough at the context around you. So that's where the weird decisions happen. Like there are methods that just look for small patches in the image and try to classify what there was. So just to give you one example, like we had in a project we were working on, we had a very strange false warning of one of our systems. So we couldn't understand why this happened, because the car said there is an yield sign and you need to stop, but there wasn't any in the scene. And we looked at the image and we saw a case where you had a like a building and a window frame, like horizontal, which was like red window frame, and there were like people walking by, and people walk and their hands do like this, and just in a couple of frames the hands of two people like form a triangle together with the window bar, and it looked like a yield sign, a white triangle with red borders, and it got detected as a yield sign. No human will do that, because you see, these are actually people, but many computer vision systems, they still look at very small patches, and to them it looks like a yield sign, and they don't get the context around you. So such things happen, and sometimes detecting faces in trees and so on. And if you only look at one small square of the tree, it kind of looks like a face, right? But yeah, it's the lack of context, from my point of view, that lead to these strange, weird decisions. But they happen a lot.
It's hard to fully predict the future. I have questions.
Yeah.
I think this can be maybe the last question. What is your day look like as self-driving car engineer?
So what my day looks like? Or
yeah.
Okay. Yeah, so it's maybe I'm not the best case, because I have some kind of mixed kind of responsibilities. But let's take a more typical engineer, is that So for example, in our project doing the localization, we have we're looking in like an agile model. So we have 2 week sprints. And in the beginning of each sprint, we have a backlog containing like all the important tasks prioritized. So the team picks, so we have teams of about 6-7 people, and the team picks a couple of tasks, and then we distribute ourselves, like usually 2 people working on one of the tasks. And you focus, it's usually mostly programming. So this is like one of them, algorithm development. So you try to solve some specific case or build on a framework. But we also do a lot of driving. So you go to the real car, to the prototype, and you try to get your newest software running there. Drive with it, you look at problems, and then try to understand them, and then upload them in the data center and then analyze further. So it's like a very iterative process. Like you try to build on top of the functions, and you have like a roadmap, and you try to build on top to advance the function. And there are, of course, like a lot of discussions with other partners, like because you have like, let's say 5-6 different inputs. You have some detections from the camera, from the radar. You need to talk to them, and define if the problem comes from them or from your algorithm. And then we do the localization. So we say where we are in the car, in the map, and how we're moving in it. And then this goes to another part of the pipeline. So they also sometimes find problems for you and come back to you, and you need to analyze. So that's more or less how it looks like. And it's an iterative process. You need to talk to a lot of people, and you need to focus a lot on the programming and specific task, and always looking on the algorithm and on the KPIs in the data center, but also looking into the car and how the car is performing. Yeah, so it's more or less it.
Yeah. Thank you so much, everyone who asked the question in the comments. It was really engaging question, and they made this event really great. So thank you a lot, and you're welcome again for our next event. Just as a reminder, DeepLearning.ai is the main sponsor of this event, and they have many courses around breaking into AI and machine learning. So right after this event, you get email from DeepLearning.ai inviting you to do a survey, and then you'll be able to get 50% off on their courses on Coursera. If you're interested in learning or starting career in machine learning, you can check out their courses. Or if you're interested directly in self-driving car, you can check out the resource that Vladimir shared in the end of the presentation, which are great, such as process specialization and Udacity specialization on self-driving car. Maybe I'll check that too. So thank you so much, everyone. I really appreciate you being here, and I would also like to express my sincere gratitude to Vladimir for being with us today and for preparing a great stuff. It was really great to just learn about self-driving car. So Vladimir, thank you for being with us.
You're welcome. It was my pleasure as well.
Yeah. So until next time, everyone, please stay well and keep running.
Thank you. Bye-bye.